Welcome to episode 1. Some long time ago, it all started with a fight between two ancient Greeks. Leucippos, your name sounds like hippo. Democritus, your name sounds like the Latin root for half. Oh yeah, how about I half your hippo and do it again? Wait, what if you just can't half it anymore? Then it would be atomos. Uncuttable. Hey, it's me, Aristotle. And because air is in my name, I think everything is made of, the 4 elements. Lol, okay. Wow, because you're so influential, I'm going to believe you. 2,000 years later. Hey, it's me, Robert Boyle, boiling water to make gold or something. Is it reversed? Oh, that says Aristotle is wrong, by the way. Okay, I'm skeptical now. Guys, be skeptical, chemists. Elements of things are probably just unmingled bodies. It's me, John Dalton, and I'm gonna publish some of these skeptical-born laws into a theory. By the way, laws are observations and theories are evidence things. Okay, back to John Dalton. All matter is made of small particles that can't be broken down. All different types of elements are distinct from one another, but identical to themselves. And atoms combine to form compounds, and chemical reactions are separating, rearranging, whatever to form these new compounds. Those are called chemical reactions. Oh my god. So part 1 of this video is basically talking about how Boyle made people skeptical and made them do experiments and evidence. And how Boyle made this theory that was proving the old philosophers correct. And this opens up new opportunities to discover about the atom. I don't know.
Yeah, okay, that's the end of part 1.
Hey, it's me, William Crooks, and I stole this chicken because I'm a crook. Hey, it's me, Julius Plucker, and I'm gonna pluck the chicken you stole. Hey, wait, we're about to make the most important study about the nature of atoms. Psst, 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 psst. Whoa, I know I stole you, but you can do what with a glass tube? Crook's glass tube. Okay, so basically in a cathode ray tube, we have the cathode and we have the anode, and we have something blocking here, and basically when high voltage is applied to this, the electrons go and simultaneously air is getting removed, but the electrons are glowing, and then they create some shadow of the mask, right? While the air is getting removed. But then if there's no air, then what is glowing? What was his name? I forgot his name. That's what William Crooks figured. Okay, bye. It's me, Jean-Baptiste Perrin, and because I'm French, I'm gonna steal your glass tube. Oh no! It hit the evil magnet I also stole. Ha ha ha! The green glow is moving. That must mean the cathode ray is a charged particle. Oh yeah. It's me, John, but not the French John, the British John, because John is my middle name. And look, if you put a magnet on the cathode ray tube, I can't say electrons. The cathode ray goes towards the positive side, meaning that the cathode rays are negatively charged. Whoa. Because I'm incredibly smart, I figured the electron to mass ratio means it's either 2,000 times more chargy or 2,000 times more smaller. But because the charge is probably the same, that means, wait, what? There's something smaller than the smallest atom. Oh my gosh, this is so crazy. It's still me, Joseph John Thomson. And after testing with different materials, I figured that this thing exists in every material. It's still me, Joseph John Thomson. And basically, I've decided that there's these little things in every atom I'm gonna call it the electron. And they're part of every atom. If there's negatively charged electrons, this is like my diagram, by the way. This is what I believe the electrons are inside the atom. If there's negatively charged electrons, that must mean there's something positive in there to balance it out. Wait, I just made the most significant, not important, the most significant discovery about the nature of the atom. So this is my diagram again, except this time these little things are negative and the thing they're in is positive. See, it's this a plum pudding. It's me, Mr. Quick Check. So basically the two most important components of Thomson's atomic theory are that there's something smaller than the smallest atom, and that atoms have opposite charges. But yeah, that concludes part 2. I wish I had some ice cream right now. Maybe Ernest's ice cream. Ha! Oh my god, it's me, Ernest Rutherford, and I'm going to Cambridge to study this new concept associated with these electrons called radioactivity with Mary and Pierre Curie, but they're irrelevant. And because I'm so cool, get it? Because ice cream is cool, I'm gonna name them alpha, beta, I don't know why it cut off, but basically the least to most piercing is the alpha helium nuclei particles, nuclei, I don't know. And then the beta electron particles, and then the most piercing is the gamma high energy waves. I don't know why it cut off when I said gamma rays, but okay. Anyway, so basically, because Thomson's model meant that an atom was uniform throughout, then when they tested the emitting of the radiation, then most of them should be linear, but some of them started shooting back, which was really weird, meaning that the atom is not uniform, and he predicted it to be dense in the center and made up of mostly nothing. So some of them would go through, and then some of them would hit the nucleus. Oh, can I say that? Well, the dense center and deflect, or come back. Yeah. It's me, Ernest Rutherford again, and I'm making the most significant contribution to the atomic structure. The atom is mostly nothing. This is a really weird drawing. The atom is mostly nothing. It's me, Mr. Quick Check again. Why did Rutherford believe the nucleus was so small compared to the size of the atom itself? It's because although most of the helium alpha particles, nuclei, I don't know, would pass through, only a small fraction would refract or shoot back. So he was oh, it probably is small. And why did Rutherford believe that the nucleus had a positive charge? Because the radioactive particles were positive, and when they hit the center, they deflected. That means that the center is positive, because like charges, both of these are positive. What's it called? They don't like each other. Oh, they repel! And that's the end of part 3. I think we're on to like the math thing now. I don't know. How can I do this? I don't know. I'll figure it out. Okay, crash course on whatever this is. Basically, this is the mass number, this is the proton number, and this is the element symbol. The mass number is basically made up of the protons and neutrons because electrons have basically no weight. And then this is the proton numbers, and to get, obviously, the number of neutrons, we could do Z minus, no, don't trust me, A minus C, and then you would get the number of neutrons. And then this is the element symbol. I think everyone knows this, I don't know. Basically, if we were to write this in my little example here, we have magnesium. Here we take the atomic mass and then we would make it magnesium 24, and the atomic mass is, yeah, it's the atomic mass unit. Give me a second. Okay, in the example there's 12 protons, so the mass of 24 minus 12 protons mean there's 12 neutrons. Is there anything else to talk about? Oh yeah, I forgot I did the ions. Okay, so basically this has 12 protons, right? But the ion has makes like this whole thing a charge of 2 plus. So if there's like, if it has a 2 more positive charge, I don't know how to explain it, that means there's only 10 electrons, because if you were to, I don't know, balance it out, cancel them, that means there's 2 extra protons. So yeah, there's 10 electrons in this magnesium cation, cat because they're positive. Ha ha ha, thanks Miss Shirley. Okay, let's use the workbook example. We have a 4 plus ion of lead-207. So if we start with lead-207, we know that it would be Pb207, right? And because we get the, thank God, the periodic table, we just have to find the atomic number for lead, which is 82. And so then we would write that in the Z spot, right? But the question is asking us how many neutrons, so we would just do this minus that, which is 125 neutrons. I didn't do that in my head. I looked at the workbook. I'm not like those crazy math people. And then we know that it is a cation with a charge of 4 plus. So 82 minus 4. Oh my gosh, why is this so hard? It means there's 78 electrons. I don't know what happened there. Okay, bye. Okay, so some elements, and I'm using my scissors this time, I'm not ripping the paper, have different atomic masses or isotopes, right? And the way they figured this out, I don't know if this is going to be on the test or not, is basically they shot them through the ray. Do we need to know what this is? And the one with the most amount of turn, this is such a bad drawing, would mean it's like the least heaviest, the lightest. So this would be like in the example neon 20, while the one that's deflected the least would mean it's the heaviest. So in this example, it would be the isotope of neon 22. Forgot this thing is in reverse. Oh yeah, this goes back to the E over M thing, the charge to mass ratio. Remember the 2000 times thing? I don't know, I just wanted to say that. Okay, bye. Whoa, but how would you calculate the atomic mass of something with like different isotopes, right? So let's use neon, because that's the workbook thing, I don't know. Let's say neon 20, the units are, for example, hypothetically, I'll just use 20, or sure, why not? 20, even though it's not, neon 20 weighs 20, even though in real life it's 19.9924, but I don't really care about that. And the amount, why do I even do this? The amount is 90%, and then neon 21 is, let's just say it weighs 21 and it's 1%. The neon 22, it weighs 22 and there's 9%, right? So to find the, like, this is split up into these three. To find the answer, we would multiply 20 times 0.9, 21 times 0.01, 22 times 9%. And then you would get the mass. Also, don't forget your units, which is AMU. Oh, I dropped it. Oh yeah, don't write it like that. To write it, you would need to do like 20 and then like 20 and then in brackets 90% plus dot 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 equals AMU. Okay. Oh, calculating isotope things, percent abundance. Okay, to calculate the isotope percent abundance, it's only gonna give us things with 2 isotopes, Mr. Toth. So it's gonna give us the atomic mass unit of boron itself, and then boron 10, and then boron 11. So what you do here is basically it's in reverse. So if we put X as like our placeholder for the percentage, then we know that like a percent of X of the isotope of boron 10, let's just put it, I'll just put 10, plus 1 minus X, because what isn't 1 is the other, and 1, because 1 in percent things is 100, I mean, or well, 100% is just 1, and X is a percent, then it's just 1 minus X, which is the other percent, equals, or well, times, this is really hard to write out, times the atomic mass unit of boron 11 equals the atomic mass of boron itself. I'll just put 10.81, what it actually is. So you'd have the atomic mass unit of boron 10, atomic mass unit of boron 11, and then atomic mass unit of boron itself. And then what we're looking for is these 2 percentages. What is this and what isn't this? Is the other this? I don't know. Basically, you do the math. You find what X is, and X will be your first percentage, and then the other percent will be 1 minus percent. Please don't mix them up. That will be pretty sad. I think we're done. End of part 4. Okay, bye.